Okay, the second group are so-called dark nebulae. And they look like holes in the night sky covered by stars. Let me just give you an example. This is an example of a dark nebula, and it's called Horsehead Nebula for obvious reason because of its shape, right? It looks like a head of the horse. So what is happening here is that, again, the dust particles in the nebula, and they are typically very dense, they block the starlight of the stars behind the nebula, so we can't see those stars. Okay, so schematically what is going on is, say, this is such a nebula containing a lot of dust. So if I have a star here, this is the direction to us, to the observer. The starlight that I'm now going to denote with yellow color is being absorbed by the dust particles. But in equilibrium, as much energy is being absorbed, the same amount of energy has to be re-emitted back in space. Otherwise, more and more energy would be absorbed, and the nebula would increase in its temperature. Its temperature would increase. Okay? So basically what is happening is that the dust particles absorb the starlight, but then they re-emit the same amount of energy that the nebula absorbed in infrared wavelengths. It's being absorbed by the dust particles in the nebula, and then it is re-emitted throughout the space in all directions in infrared. Often we use the acronym IR for the infrared. Okay? So basically, the dust particles absorb the starlight, and then they re-emit the energy at infrared wavelengths. Right? I mean, you know, you can, if you have a bucket and you pour in the water, you can put in only so much, right? Unless you drill holes so that that water can come out, right? So then you have, so if as much water comes in, the same amount of water comes out if you do it right. The same is here. Sort of water coming in, you have sun, or rather starlight, coming and being absorbed by this dark nebula, by its dust particles. And then it releases back the energy, but at infrared wavelengths. So in principle, we could observe dark nebula at infrared wavelengths. Of course, we need special detectors that are sensitive to these very long wavelengths, infrared detectors. Okay, and if you watched many action movies, you see, you know, soldiers in some action, like the one that won Oscar a year ago, Zero Dark 30, right? When they were going after bin Laden, all the commandos had these infrared goggles that are sensitive basically to infrared, because humans, our body temperature is about 37 degrees centigrade, and it turns out that as a result of that, we emit most of the energy at infrared. Those of you who took Astronomy 1P01 will recall that the wavelength at which a body emits most of its energy depends on its surface temperature, right? And the hotter it is, the shorter the wavelength where most of the energy is emitted. For temperatures like human body, right, and these relatively cool nebulae, they emit in the infrared of that same Horsehead Nebula, but in infrared. Okay, so now of course our eyes cannot detect infrared, but the colors are artificial, right? The red suggests that basically it's infrared, right? But you can see the difference. This is what we observe at visible wavelengths, basically nothing, because the starlight of the stars behind the Horsehead Nebula is blocked by the dust in the nebula, but that nebula then re-emits energy at infrared wavelengths. When we observe it at infrared, we can actually see that indeed it emits at infrared. Okay, the goggles that soldiers wear work in the same way, right? They just electronically change the color, right? So the people don't, when you view things through those infrared goggles, right? The shapes are rendered electronically, right? But based on the infrared radiation that they emit.